Great, thank you so much, Jose. Yeah, first of all, I'd like to thank the organizers of the event for organizing this conference with very excellent researchers and very interesting topics. And I'm glad that I'm here to present my research today. So today I'm going to talk about this paper that I put out with my supervisor earlier this year. It's called The Geometry of Spacetime from Quantum Measurements. And hopefully the idea will become clear throughout the presentation. So in this talk, first we're going to review spacetime separations in general relativity, just in classical general relativity. Then we will talk about how it's possible to rewrite or rephrase the geometry of spacetime from the correlation functions of quantum fields. Then we'll talk about how to physically access these correlation functions and to really measure them and obtain them experimentally, if you will. And then finally, we'll connect the idea of relating the geometry of spacetime with quantum correlations with the idea of measuring the correlations so that we can recover the geometry from measurements of quantum fields, essentially. So classical general relativity is essentially a theory for spacetime that formulates spacetimes in a 3+1 dimensional manifold with a Lorentzian metric G. And one of the things that this Lorentzian metric G, or the most important things that you can do with this metric, I would argue, is to compute distances and time separations essentially in spacetime. So I'd like to say that at its core, general relativity is a theory for rulers and clocks. And this is one of the fundamental outputs of the theory, or the predictions of the theory. And there's also another way of rephrasing, of rewriting essentially this notion of the metric and spacetime, which is in terms of Synge's world function. So essentially, Synge's world function, it returns 1/2 the geodesic separation between 2 points. So it takes 2 points as input, and it returns 1/2 the squared geodesic separation between these 2 points. And essentially, this function contains all of the information about the geometry of spacetime. It's locally defined, but essentially, so is the metric. It gives local information about the geometry. And you can completely recover the geometry from Synge's world function. So for instance, if one wants to recover the metric of spacetime, that would be given by taking partial derivatives with respect to the different arguments of Synge's world function and taking the coincidence limit. That with a minus sign would give the spacetime metric. So in this picture of general relativity, where the metric gives spacetime separations or provides this notion, you can also equally well replace this metric with Synge's world function. So this geodesic distance between the points. And the only thing is that, of course, we know that general relativity is a classical theory. So essentially, at its core, it's a theory for the measurements that come out of classical rulers and clocks. And essentially, we don't expect general relativity to be able to give a notion of spacetime when quantum effects are relevant close to Planck scale and things like that. So one of the ways to talk about space and time separations in scales where quantum field theory is more appropriate for talking about these phenomena than general relativity was presented in this reference here by Professor Achim Kempf. And I'll now try to explain what is the idea, but the goal is essentially to rephrase notions of space and time separations in general relativity in terms of correlation functions of quantum fields. So the idea is, well, let's consider a quantum field theory in a curved spacetime in a given state. I'm assuming the GNS representation of the state, so I can talk about the cat here. So and of course, there will be this correlation function associated with the quantum field, the Whiteman function, which essentially tells you how much measurements at the event X are correlated with measurements at the event X prime. And the idea is that we can use this Whiteman function in order to infer or even rephrase the geometry of spacetime. So physical states in a quantum field theory must satisfy the Hadamard condition. When I say physical states, I mean states with a renormalizable stress energy condition. And this Hadamard condition is something that showed up already before in the conference in previous talks. So I'll just briefly review it. So essentially it states that the state must be quasi-free and that the Whiteman function behaves locally as this expression here, which, to be honest, the only thing that will really be relevant for us is the fact that when the points x and x prime are sufficiently close together, this expression here becomes simply 1/8 pi squared and 1 over this 1/2 geodesic distance between the 2 points, essentially. So what one can do here at this point is to actually invert this equation so that we obtain Sinja's world function, now written in terms of the correlation function of the quantum field. So this allows us to sort of have this infinitesimal notion of space-time separation between two events in terms of the correlation functions or of the Weikmann function for the quantum field. And if we use the expression for the metric in terms of Sinja's world function from before, we can actually write the space-time metric in terms of mixed partial derivatives of the correlation function of the quantum field. So this is essentially the idea that was presented by Professor Kempf in this work. So essentially, the idea is that this expression or these concepts, the correlation function of the quantum field, can be used to define space-time separations in scales where quantum field is valid, but general relativity is not expected to be valid. So that's the overall idea. But now, what we're interested here is essentially it's not only in talking about the possibility of using the correlation functions to rephrase or define a notion of space-time separation, but how to actually access them. So essentially, the question we want to ask here is how do we access the correlation function, and whether it's possible to recover the geometry of spacetime or information about the geometry of spacetime out of probing quantum fields, essentially. And so how do we access the correlation function? The answer is essentially we need probes. We need some sort of localized systems that will couple to the field, extract information about the field, then manipulate this information somehow, and then infer the correlation function of the field. And the probes that we're going to be using here will be particle detector models. This is a very useful tool in fields of relativistic quantum information and in order to talk about information processes in quantum field theory. And so in order to introduce particle detectors, I like to bring this sentence here from the manuscript that's cited below. So I'm just going to read it for you. From the retinas of our eyes to the solid state center source in the LHC, we never measure a quantum field, if not by coupling something to it. And particle detectors are the theoretical framework for the something that we have to couple to quantum fields in order to extract local information from it. So broadly speaking, or in general, these particle detectors are localized, non-relativistic quantum systems which couple to a quantum field. We want them to be localized so that we have access to local information about the field. It's important that they are non-relativistic quantum systems so that we can actually apply our tools from quantum information theory and perform measurements without worrying about causality for the quantum field itself. And of course, we wanted to couple to the quantum field because we're interested in extracting information from it. So the simplest particle detector model that there is the two-level UW model. It's essentially a two-level system, a two-level quantum system that undergoes a time-like trajectory, z of tau. And it's got free Hamiltonian with the energy gap omega. So this is the detector itself, the two-level quantum system. And interaction with the quantum field is prescribed by an interaction Hamiltonian density, by this interaction Hamiltonian density here, which has essentially 4 elements. One of them is the quantum field. The first element here is the coupling constant. So it's simply a real scalar that's usually assumed to be small so that we can do a perturbative analysis with this. The second one is the spacetime's mirroring function, which localizes the region, the interaction region in both space and time. So it gives the shape of the detector, and at the same time, it also tells us for how long the interaction happens. And finally, this last element here is the monopole moment of the detector. So it's simply an observable in the detector's Hilbert space that doesn't commute with the free Hamiltonian. And it's important so that it doesn't commute with the free Hamiltonian so that it can actually promote energy level transitions in the detector. And this means that the quantum field can excite the detector so that we can infer properties from the field by reading the detector. So it's important to say that this UDW model, even the two-level system, is not merely a theoretical idealization. So it can actually model or mimic many physical interactions by picking the appropriate space-time mirroring functions. So for instance, it can mimic the light-matter interaction if the space-time mirroring function is associated with the atomic orbitals and things like that. It can also mimic the interactions of nucleons with neutrinos. This is something that I have been working on over the past 2 years. But overall, these models can be related to experiments into physical systems that couple to quantum fields. So back to our main goal, which is how do we access this correlation function using now these particle detectors. So it's possible to recover the correlation function of the quantum field using detectors that interact with a sufficiently localized interaction. There are essentially two cases if we want to recover the correlation function between 2 points. So one case is when the events are time-like separated. So if you have events x1 and x2, which are time-like separated, then it's possible to approximate the correlation function of the field between these 2 events as being the excitation probability of one detector that goes through the 2 events and interacts around these 2 in a localized manner, subtracted from the probability of the excitation probability of the detector after only interacting at x1, and subtracted from the excitation probability of the detector after only interacting at x2. So you get one detector that goes through both events, and then you're able to approximate the correlation function of the field. For space-like separated events, you need 2 detectors. You can't have a detector going through 2 space-like separated points. And in this case, what happens is that the correlation function of the field can be well approximated by the correlation function of the monopole moment of the detectors. One of the detector that interacts at 1 and the detector that interacts at 2. Again, in very localized regions around these events x1 and x2. And it's important to mention that these results here are exact in the limit where the interaction region is really a point like delta centered at the event x1. So these become approximations only when these interaction regions are finite, and then they are controlled by the size of this interaction region, essentially. So overall, we can use the detectors to recover the correlation function for time-like and space-like separated events. And if we can do that, this means that these detectors can be used to recover the space-time geometry, right? Because we just said that the geometry can be recovered from the correlation functions of quantum fields. So in order to do this, if we want the metric locally, we need to consider a lattice of particle detectors. The way to build this lattice is as follows. So these blue regions here are the localized interaction regions where each detector will couple. And this represents a space slice where these detectors will couple for the first time. Then the detectors will undergo trajectories in space, so in spacetimes. So they will be evolving in time. And then after some time elapses, all of these detectors will interact again and again and again. And then overall, what you get out of this is an effective space-time lattice that contains the interaction regions of each one of these detectors. And this lattice can induce a coordinate system in many cases. I mean, locally, you can always find coordinate systems that will contains at least bits of this lattice. And the idea is that we will recover the metric of spacetime in the coordinates that are adapted to this lattice. So essentially, coming back to the expression that we had that related the metric of spacetime with the correlation function of the field. Now, if we only have a discrete lattice, then we cannot really perform these differentiations or this limit. But what we can do is to use a finite distance approximation between the events. So essentially, instead of we use a finite comparison of the White-1 function, a finite derivative, discrete derivative, essentially, by shifting it in the corresponding lattice directions. And all of these W's here are the White-1 function that can be obtained from the measurements of the detectors. So this allows us to write the space-time geometry in terms of outcomes of measurements of these local probes that we use to probe space-time. So we did many examples, and all of them worked. We considered inertial detectors in Minkowski space-time, and whenever the separation between the detectors was small enough, we would recover the Minkowski metric. We did the same in many different cases, and even others that are not like explicitly pointed out here. Overall, it always worked. The detectors could accurately recover the metric of spacetime. So in summary, the things that we discuss here are that, well, classical general relativity is a theory for measurements of distances and time based on classical rulers and clocks. And but in the smallest scale, general relativity is expected not to provide an accurate description for spacetime. So, but in these scales, we can use quantum field theory or the correlation function of quantum fields in order to define infinitesimal or local spacetime separations. Then these correlation functions can be accessed by particle detectors. So essentially, we can use the particle detectors to accurately determine the geometry of spacetime. And then finally, I'd like to advocate for the fact that particle detectors can be used to define a quantum notion of rulers and clocks, which hopefully, which I think is the first step in order to start talking about a quantum notion of spacetime. So thank you so much, and I'm willing to take questions now.
Okay, thanks for this inspiring talk. And well, questions? Yeah, Ivan, there is a question here from Ivan.
Hi, thank you for the talk. It was very interesting. But my question is that, you know, as you explained very nicely, the Hadamard condition gives you some universality of the divergence terms whenever the 2 points get, you know, get coincident. But at any finite, at any non-zero separation, the properties of the state can actually mask, you know, can be larger than the Hadamard in the Hadamard term, because it's really an asymptotic condition.
Yes.
So if you really measure things at a finite distance, how can you be sure that you are not really measuring the properties of the state in particular and not the Hadamard dominant term? So
I mean, if it's close enough together, like the main diverging term here is this 1 over sigma. So you're always going to be able to write this in the limit, right? But in fact, if they're not infinitesimally close, you will get contributions from the state dependent part, right?
Right.
But maybe this is a good feature of this formulation, which is that the state of the field actually would change the local notion of the metric that emerges out of this sort of formulation here, essentially, which would be, you see, because if the quantum field is in a given state that produces, for instance, a T mu, right, then the metric of spacetime will also change due to that. And then maybe these effects are also contained in these extra terms that are state dependent in the Whiteman function. But again, this is all very early work and things that we're doing right now. But the idea is that these terms should somehow contribute to how spacetime behaves given the state of the quantum field. That would be my answer to that.
Thank you.
Okay. More questions or comments? Peter Taylor? Yeah, okay. Okay.
Hi, yeah, excellent talk. Thank you very much. Kind of a similar line of questioning is what about the dependence on the mass and the coupling of the field?
What do you mean dependence on the mass of the coupling?
Well, your Whiteman function is going to depend on the mass of your field and on the coupling of the field to the background curvature, for example.
Yes, that's true. It does depend on the examples that we did. So the first example that we did actually, which is this one essentially, we considered a massive field in Minkowski spacetime, right? And we considered inertial detectors just like evolving freely, probing this quantum field, separated by distance L, right? And what happened there was, if this distance was small enough, the effect of the mass, essentially, you see, if the distance is small enough compared to 1 over mass, essentially, then the effect of mass would not influence the weight. Then we would be able to accurately recover the metric of spacetime. That's which is the 1, 0, and -1 for the diagonal and off diagonal terms, right? So the mass does play a role, right? But at the same time, we know that the mass plays a role in the stress energy momentum tensor of the quantum field. So we would expect that a massive field in Minkowski spacetime would have an effect in the background geometry as well. So maybe there is a correct distance for you to pick such that these estimations of the metric coefficients would be the ones that would also emerge out of Einstein's equations by considering a massive quantum field.
Right. So your notion of your distance being small enough is related to, it depends on the mass of the field you're considering.
Somehow you're going to need a scale, right? Because if you don't have any scale, small doesn't mean anything. So for instance, in this case here, we considered accelerated detectors in Minkowski, but a massless field. So the scale is actually given by the acceleration of the detectors, right? Or the acceleration of one of the detectors, one of the trajectories there. In the Sitter space, it's the curvature radius, and when you have a massive field, it's the mass. And funnily enough, if you apply this formulas here if you use this discrete derivative method here for a massless field in Minkowski spacetime with inertial detectors, this actually gives the exact results of -1, 0, and 1, because it's a quadratic thing once you invert the Weitman function. So this actually becomes exactly the 1 minus 1 and 0, right? So it works exactly if you have no scale. If you have scales, these scales starts blurring a little bit your estimate of the real metric, or giving some non-trivial features that we're currently exploring. So yeah.
Yeah. Okay. Thanks, Rick.
Okay. Any other question? Okay. Well, may I ask one?
Yeah, of course. Yeah.
If we introduce interactions, I mean, not a free field, but just a field with self-interaction, that is going to change the picture somewhat, or?
Well, that would definitely change the picture. I'm definitely not clear exactly how it will change the picture. We're trying to incorporate these things into these ideas right now. Also, which correlation functions, right? Which would, like, say that you have fields phi1 and phi2. So if you consider the correlation function associated with the field phi1 and the one associated with the field phi2, would you get two different metric estimates or something like this? And also depends on whether the interaction is weak or strong. So the short answer is we don't know yet. We're currently looking into it.
Okay. Okay. Thank you. Thank you for your very nice.